Hi, my name is Sina Ahmadi, and I'm glad to be presenting my paper entitled Towards Machine Translation for the Kurdish Language in the third workshop on technologies for machine translation of low-resource languages. My talk is mainly composed of three parts. I'm going to go through an introduction and the objectives of these projects, and then provide a description of the Kurdish language, and finally describe the systems that we created using neural machine translation for the Kurdish language. So machine translation is one of the major and most important subfield in the natural language processing field, where we deal with translating different texts from different languages. But this field is not equally accessible and addressed for all languages, particularly due to being less resourced. We have many languages which are less resourced. There are not many data sets available for them. But also some language-specific features makes the machine translation task particularly challenging, for example, for morphologically rich languages. And another issue is the availability of basic NLP tools like a tokenization system, which can be integrated in the pipeline of creating an empty system. Our objectives is first of all to describe the Sorani dialect of the Kurdish language, some of its linguistic features, and then shed light upon the MT task for Sorani by creating a basic setup for processing the language, particularly creating a tokenization system, and then build and evaluate a neural machine translation system for Sorani Kurdish. A bit about the Kurdish language. It is an Indo-European language spoken by 20 to 30 million speakers in the Kurdish regions of Iran, Iraq, Syria, and Turkey, and also among diaspora, the Kurdish diaspora. It is mainly written in two scripts, a Latin-based one and an Arabic-based one. The Latin-based one is mostly used for the Kurmanji dialect, while the Arabic-based one is mostly used for the Sorani dialect. The Kurdish language is a less resource language, meaning that there are not many tools or resources available for processing this language automatically. So as you see in the diagram and the schema, there are four dialects or languages for Kurdish: Laki, Southern Kurdish, Central Kurdish, Northern Kurdish. We're focusing on the Central Kurdish or Sorani in this paper. And the reason mainly is that in 2016, Google, the translation service of Google, added Kurmanji Kurdish to its list of languages. Then we decided that we would explore the Sorani dialect in this case instead of Kurmanji, even if the Kurmanji one is not also that much explored. Overall, there are not many studies addressing Kurdish machine translation, except a few attempts by, for example, the project Apertium, where a rule-based system is implemented for Kurmanji and Sorani. There's also an online service called In Kurdish, which has a dictionary-based machine translation service. And also, after this project in August 2020, Microsoft Translation Service added Sorani and Kurmanji happily to their service also. Studying the related literature, we can see that there's still a long way ahead because it is not explored enough this field for the Kurdish language. So a bit about the Sorani Kurdish dialect. So it is mostly, as I said, written in the Arabic-based script. It is vastly spoken in the Kurdish regions of Iraq and Iran. It has a split ergative system also, where transitive verbs in the past appear differently from intransitive verbs, particularly in Kurdish using different pronominal clitics, which are highlighted in red in the examples. Kurdish has a complex morphology, particularly due to many clitics, affixes, and the way that they appear within the sentence. So we are gonna describe our experiment settings. We first prepared our data sets. We mainly used the Tanzil corpus, which is a collection of Quran translations compiled by the Tanzil project. There's one single translation in Sorani, which is aligned with 11 translations in English, making 92 parallel sentences with over 3 million words in the Sorani side and over 2 million words in the English side. It is a religious text, so it has a lot of text in Arabic, a lot of interpretational footnotes provided within the text by the translator, and also it has also some inconsistencies in writing. For example, the word load is written by the Arabic spelling and not the Kurdish one. We had to use this corpus because this is the only large corpus that we could find, the only parallel corpus that we could actually find with this size, even if we were sure about the quality of the translation and also the fact that this is very domain specific within, it's a religious, it has a religious context, so it may not be ideal for general domain or general purposes. Then we have the TED corpus, which has a wider range of topics, but it has an issue with the length of the sentences. The alignments are not very precise in such a way that we found many sentences aligned together instead of one. And then finally, we had the Kurdish WordNet, KurdNet, which contains 4,663 definitions translated from the Princeton WordNet into Sorani Kurdish. So as I mentioned, we have an issue in these data sets with the length of the alignments. In the Tanzil one, it's reasonable in some ways, as we have something around 25 tokens per alignment. But in the TED, we can see that the English side contains 93 and the Kurdish side 69. So you can imagine that each alignment in the TED corpus is so huge, it's a bulk of text, a chunk of text. While in the KurdNet we have short sentences, but they are domain specific and the words are more technical. Regarding the data preparation, we pre-processed the text, removed non-relevant characters, cleaned the data, removed interpretations provided within parentheses, unified the encoding of the characters, which is an important step in Kurdish language processing, and then we normalize orthography. For example, the initial r, which should be written with a specific grapheme. And also, regarding English, we true cased and removed interpretations within parentheses. One main issue that we had regarding this project was that we didn't have basic language processing tools for Kurdish, so we had to create a tokenizer ourselves. For this purpose, we used unsupervised methods like wordpiece, unigram, byte pair encoding, and wordpunct. Wordpunct is the NLTK simple punctuation, separation, and splitting by space. But these took a bit of time because we had to train models and create data sets. On its own, it was another project really, but we managed to create these 4 models and create these 4 models for our data sets for training, testing, and validation. So regarding the NMT models, we created 2 models using the PyTorch version of OpenNMT. We use sequential sequence-to-sequence NMT models. So the first model is a very simple 2 LSTM layers with 200 hidden units, both for encoder and decoder, while the second model is the default OpenNMT model as of August 2020. The details are provided in the paper. Regarding word embeddings, we use fastText for Kurdish and Glove for English. For the evaluation purpose, we use 3 metrics, BLEU, Meteor, and TIR. As I mentioned, we created various data sets based on the tokenization techniques. So we evaluated different tokenization techniques. And we and also, as the Tanzil corpus is remarkably larger, we split the whole data sets into two parts, calling test 1 and test 2. In test 1, we set 10% of each data set aside, while in test 2, we merged everything together and then split it into training, test, and validation sets. So this way we will have a better insight into how the final model will perform on each dataset individually. Regarding our results and analysis, the quantitative analysis showed that in both Kurdish to English and English to Kurdish translations, the word punk performed better. And surprisingly, Model 2, we expected it to be more robust, but it performed only better on the English one. And in test 2, where we merged all the data sets together, all the setups failed to translate KurdNet and TED due to imbalance of the data. The Tanzil corpus was huge. And then the type of sentences that we also have in KurdNet and TED, where they are more technical, they're not in the same field of the religious context of Tanzil. And the length of the alignments in TED would also be an issue to explain such poor performance. Regarding the qualitative analysis, the system translations carry meaning in a comprehensible way. And we also observed that the models captured synonyms and words which were closely related semantically, like the words zanist and zaniari for science and knowledge. And overall, the whole output of the systems looked legible, and it was not just nonsensical, but it was obviously not. In most cases, it did not. The system outputs did not correspond to the reference. So in this paper, we presented machine translation system for the Sorani Kurdish language. This was the first attempt to use neural machine translation for this language, as far as we know. We observed two main limitations regarding the current work. First of all, we didn't have a baseline system, and the reason was that the previous, particularly the rule-based Apertium translator was not operational, so we could not get the baseline results. And then we did not extend our experiments to further hyperparameters to explore further hyperparameters. As future work, we believe that extending this work to other dialects of Kurdish and also using morpheme-based translation and sequence-to-sequence pre-training techniques and also lexicons will be beneficial to pave the way for more robust systems for the Kurdish language. Our models and data sets are available here, and would thank you for your attention.